everyone. Welcome to the another session of digital signal processing. We had started talking about DFT in the last session. So continuing to that discussion, today we are going to discuss one important property of DFT, that is circular convolution. So we'll be covering difference between the circular convolution and linear convolution, and then we'll be discussing three different methods of carrying out this activity, circular convolution by DFT, which is also called as Stockholm method. We'll also discuss how to calculate this by graphical method, and another method for calculating this circular convolution is matrix method. So first of all, what is a linear convolution? As we have been studying any kind of mathematical operation in signal processing, we have to perform this convolution, which is a combination of three tasks: folding, shifting, and multiplying. So these three operations make up the final output that is called as the convolution of two signals. An application of this convolution is generally finding the output of a system. So if I have any system represented by some transfer function Hn, and I'm giving certain kind of input x into it, and I want to know what would be the output or response of this system corresponding to this input xn, then I simply represent it as convolution of input signal with the transfer function of this system through which I am passing this signal or processing this signal. So I have to perform folding, shifting, and multiplying. That means if I define this convolution signal yn output, it would be summation of xk and h of n minus k. It may range from certain value, say minus n to n. So that means this is certain value of xn at n is equal to k at any sample point, and the second signal, this transfer function signal which is being represented by hn, this k has been folded, the k has been converted from k to minus k, and plus n has been added here. So we represent it as n minus k. So this is like folding. When I am adding n, this is shifting, and when I am multiplying these two signals, it is multiplication. So this is, the definition says, folding, shifting, and multiplying. This operation gives me the output of a system represented by Hn when input xn is given to this system. And when we talk about circular convolution, this again involves these three steps of shifting and multiplying and folding. So what is the difference between two? The characteristic lie into the signal. The signal that we are giving here, that is the xn to my system Hn, the special property of this signal is that this signal is periodic. So as we have discussed in the properties of DFT, that DFT is periodic and it is applicable on finite length sequence. So we are saying this convolution corresponding to DFT as circular convolution. So shifting can be thought here as rotation. Why rotation? Because the sequence xn, first of all, it is finite and it is periodic. So when I am shifting it, and if it is periodic with period n, if I shift the sequence n times, then I would get the same sequence after n shifts. So a periodic sequence, a sequence which is having finite number of samples in this particular sequence xn, the shifting is equivalent to rotation, and that's why the convolution that we perform here is called as circular convolution. Secondly, another difference between linear and circular convolution is how do I represent it. So when I have to convolute two signals linearly, I use a symbol star here where yn is the output, xn is the input, hn is the transfer function of any LTI system. And when I have to represent circular convolution, I use this plus sign encircled by this ring. Again, yn is the output, xn is the input, and hn is the transfer function of the system. So the basic difference in representation is of star and this plus encircled by a ring. Another difference between this linear convolution and circular convolution is when I perform this linear convolution, two sequences xn and hn, they may or may not be of equal sizes. Sizes means how many number of samples do I have in it. If I count for xn, the number of sample is 3. If I count for hn, the number of samples are 5. So this is the particularly length of the sequence. So these length can be same, these length cannot be same. There is no compulsion. So total output which I get here, the length is the length of first sequence, the length of second sequence minus 1. 3 plus 5 minus 1. The output sequence would have number of sample equal to 7. So these two length may be equal, may not be equal, but particularly talking about the circular convolution, the length of these two sequence must be equal. That means if these two lengths of the sequence is there, 3 and 5, then I cannot perform circular convolution. I have to make these sequence equal in length. So what do? I insert n number of zeros so that the length of two sequence becomes equal. And this process of adding extra zeros is called as zero padding process. So the compulsion is whenever I am carrying the circular convolution, I have to make the sequence of equal length, or I have to take a sequence which is already equal in number. So if xn has a length say 5, hn is also having a length 5, ultimately the output sequence would also have a length 5. So all these three sequences in circular convolution would be of equal length. So these are two differences between linear and circular convolution. And let us now learn different techniques. How do we carry out circular convolution? So I have given two sequences, x1n and x2n. Here I can see the length of both the sequence is equal, so there is no need of zero padding. I can apply linear convolution as well and circular convolution as well. So in linear convolution, either I can go by formula or I can use the tabular method for calculation of linear convolution of x1n, which is representing in this row, x2n, which is representing into the column. So multiplying all the component one by one, 1 into 1, 1 into 1, 1 into 2, 1 into 2, and so on, I create this table. Then I would start adding elements diagonally and I would receive corresponding output of the sequence, which would have in the linear convolution, because length is 4, second sequence is 4 minus 1. 7 number of element in the output sequence. Or if I don't want to solve it by this tabular method, I can simply use direct formula, multiply all the samples one by one and calculate it sample by sample. So these are two techniques by which I calculate the linear convolution for a given sequence. Now I need to find the circular convolution as well. Here it has been specified that I have to use DFT and Idft method, which I was telling you is also called as Stockholm method. So let us solve this same numerical with three different type of circular convolution type. First is by the formula, in which I would take first sample and shifted second sample and would start multiplying it one by one. This particular representation is for circular shifting. So whenever I am circular shifting any sequence, I would have to either represent it as this, or another format of representation is I would simply write modulo n here. So not much difference, just representation difference between the linear convolution and circular convolution. So what I see when I talk about this circular convolution, these points I obtain, that is x2 zeroth element, modulo 4 is x2 0. If I talk about minus 1, it is equal to x2 3, minus 2 is equal to x2 of 2, and minus 3 is equal to x2 of 1. This is by substituting different values of n into this formula. So I can calculate all these samples by simply shifting the another sequence, taking different samples of 1, 1, 2, 2 and 1, 2, 3, 4. So this is a direct way of calculating the circular convolution. Another method is the graphical method. In the graphical method, what I have to follow, I have to create these two different circles. one for sequence x1n, another for sequence x2n, and I have to plot these points at equal distance. If I have 4 samples, I'm starting and making these 4 points in the x1n sequence, 4 points in the x2 sequence. If I have 8 samples, then I would again cross them here in between. So distance should be equal between every sample. But here we are solving for 2 sequences, 1, 1, 2, 2 and 1, 2, 3, 4. This is say x1 and this is say x2. So how to start? This is x1n. Starting from here, I have written x1 0. The first sample is here. x1, second sample, third sample and fourth sample. So this is writing the element anti-clockwise. Similarly, I would write the second sequence, first sample 1, then 2, 3 and 4. So both have been written in anti-clockwise order. The second step is, keeping the first sequence constant, I would fold the second sequence. That means if I have written x2 in anti-clockwise, now I would write this sequence clockwise. This is what I called as folding property. So here I got x1n and here I got x2 minus n. Folded sequence. So folding has been performed. The second step would be multiplication. So this sequence and this sequence would be multiplied point to point. That means this position element and this position element would be multiplied. Similarly, the position of this element and this element is same. They would be multiplied. So when we start this multiplication, I get the first stage of sample, and adding all these 4 points which I am multiplying, I am getting the first sample, which is the convoluted sequence. So that was for n is equal to 0 when no shifting was performed. To calculate n is equal to 1, I have to shift this sequence by 1. So this second sequence would be rotated 1 step anti-clockwise. So here this first sample would now be coming here, this second sample would come here, third would come here and fourth would take the place of the first. So keeping x1 constant, I am rotating this folded x2n 1 step anti-clockwise direction, and I would again multiplying this shifted sequence with the original sequence point by point, and adding all the 4 points would get the second point of convolution. Similarly, I would keep on performing this step till I don't get the same sequence again. And because the period or number of samples in this sequence is 4, I have to perform this process 4 times. Once I have processed this 4 times, I would again have the same sequence and the pattern would start repeating. So I would get 4 samples in the output, and that would be the final circular convolution that I have obtained for these sequence using this graphical method. Stuckham method is directly based upon the DFT and Idft process. So this is basically based on the convolution theorem, which says if I am able to calculate convolution in time domain, and if I am taking the Fourier transform, discrete Fourier transform of both the sequences, then convolution in the time domain is equal to multiplication in the frequency domain. So here I am talking about circular convolution. The same algorithm would be applicable. I would calculate x1k corresponding to x1n. I would calculate x2n corresponding to this x2k, and then multiply these transformed sequence. So this convolution is equivalent to multiplication in the frequency domain. Now how to get this x3n out of these? I would simply take inverse DFT for this multiplied sequence. Say I am giving it a name x3k. So inverse DFT of this multiplied sequence x3k would give me x3n. So this would be my final circulated convoluted sequence. So I'll be using the formula direct DFT formula, and finally I'll be using Idft formula of substitution for the same sequence that we have seen. So sequence has n is equal to 4. For k is equal to 0, I'll solve for n 0 to 3. For k is equal to 1, I'll be solving this summation for k is equal to 2 and 3. So this is my first sequence x1k. Similarly, I would calculate the second sequence using DFT, that is x2k. I would multiply both the sequence to calculate x3k. Now I need to calculate time domain samples. So I would take inverse DFT of this sequence. Repeating this process again, I would get all the samples. So I can see I am obtaining the same samples, that is 15, 17, 15 and 13, which is same which I had obtained by the graphical method as well. So these are different techniques by which we are solving this circular convolution depending upon the choice and comfort of the user. The last method is using this matrix method. So here two matrices have been plotted, in which one is the shifted sequence X and another is a single column matrix of H, and I am performing the matrix multiplication. So this component being multiplied the first component, this is multiplied with the second component and added together gives me y0. The same process is repeated for all the samples. So for the given numerical, if I try to solve it using matrix method, what I have to do, I have to create three matrices, one for x1n, which would have 1, 1, 2, 2 samples, and the matrix would be created as I would take 1, 1, 2, 2, which is this particular column. Then this last element is the first element of the another column. So I would write 2 and all these remaining constant 1, 1 and 2, again 2 and 1, 1 and 2. So this would keep on repeating till I get the same sequence again. And this H is my 1, 2, 3 and 4. When I perform the matrix multiplication row and column wise, I would get my yn. So this is how I solve the convolution using the matrix method. So either it is specified how to solve the circular convolution, or depending upon the ease or comfort, I can solve it using matrix method, Stockholm method or by graphical method. So these were three techniques by which we can calculate the circular convolution for another sequence which is periodic and finite in nature. So in the next session, we'll be discussing about how to convolute long sequences or other very long sequences which may not be possible by using small length register. This is all for this session. Thank you.